Okay, it's time to start. It's my pleasure to chair this session. My name is Eugenio Guglielmelli from Campus Biomedical University in Rome, Italy. And this session is, as you know, on manipulation and grasping. It's the third session of the series and parallel robotics as well. And it's my pleasure today to introduce you our keynote speaker, Dr. Oliver Brock. He received his master degree and PhD at Stanford University in California under supervision of Professor Khatib, and he has been working as a researcher and professor and teacher in the US at Stanford as well, Rice University, Amherst University in Boston, and he has been back then to Germany at TU Berlin, where he is Alexander von Humboldt Professor and Head of the Laboratory for Robotics and Biology at the Faculty of Electrical Engineering and Computer Science. He is a very well-known scholar in the field of motion generation planning and also, of course, on manipulation and grasping. That is the topic of his talk today about, as you see, grasping and manipulation by humans and by robots. I leave the floor to the speaker, please.
Thank you very much for the introduction, and good morning, everybody. It's almost exactly 2 years ago, at this very conference, at a plenary talk, that one member of our community proclaimed that grasping is solved. I'm glad that there are some chuckles in the audience. I really thought hard about this over the last 2 years, and I'm glad to report that now, 2 years later, I have come to the conclusion that grasping is not solved. Thank you. And actually, I want to substantiate this. An obvious way of assessing this is to watch the gap of performance between human manipulation and robotic manipulation. But there's actually another gap, which is how humans and how robots perform manipulation. In order to make that point, I would like us all to look at a brief video of a very simple grasping task, a human picking up a block of a table. If you watch this in slow motion, we will see that actually a lot of things are going on even in this very simple grasping action. So first, the fingers contact the table, not the object itself. Then there's a sliding motion of the object until contact is made. Then basically the fingertips roll around the object to lift it up and to get contact with the bottom edge of the object. And only then do we achieve some sort of force closure and lift the object. So this is a very, very simple grasping action, but we already see that there's a lot of interaction between hand, object, and environment, right? This triangle of hand, object, and environment that takes place. This is a very simple thing. If we look at some of the things that humans can do, we have to look at Julia Child. And again, Matt Mason, 24 hours ago, was standing exactly here. He also showed a video of Julia Child, which is a TV host of a cooking show. And he showed this short 7-second sequence of potato cutting. I pointed out when we were picking up the block of the table that there's lots of interaction between hand, objects, and environment. And so we've actually annotated all these interactions in this video. You don't really have to read everything. The idea is that the potatoes are being slid across the table, the knife is sliding against the knuckles, rotation of the potato is performed around an edge contact with the table, and so on and so forth. So in this 7-second segment, there are 35 of these interactions between hand, object, and environment. This is very, very different from how we as roboticists perform grasping on robots. We don't really deal with these interactions between object, hand, and environment, but my point is going to be that I think we should. So these interactions, I refer to them as environmental constraints. Right? The environment is constraining the motion that we're performing in some way. And basically, my hypothesis for this presentation is going to be that these environmental constraints are very important for robustness in grasping and manipulation. So if this hypothesis is true, right, if these environmental constraints are so important, then the following should also be true, right? If this is true, we should be able to show that humans deliberately and purposefully use these environmental constraints. If this is in turn true, we should start thinking about building hands very differently. We should start building about hands that are very competent at making contact and maintaining contact and guiding this sliding motion, this contact motion between hand, environment, and object. And once we've built these hands differently, I will show that all of a sudden, all that we know about planning algorithms has to change, right? And also the way that we perceive the environment has to change. So in this presentation, I want to go through all of these points very briefly and sort of give you an overview of the work that we're doing in our lab. So the first point is we would like to demonstrate in humans that they use these environmental constraints during grasping. So the idea is that we have a bunch of humans in constructions like this, and the video is supposed to play. And the experiment is very simple. We just reveal an object that's placed on a tablet, on a touch screen. The person picks up the object, and you see that the tablet is mounted on a force sensor. We can obviously identify the contact on the surface. We have 3 cameras watching this, and the person is strapped into some contraction to make sure that we eliminate as many of the variability as possible to just focus on how these environmental constraints are being used. We do this with 10 different objects, which we've painted black to ensure that really it's only the shape that matters and there's no learning based on color. And then we put them these goggles on that sort of have a shower curtain type glass in them. So through these glasses, the objects look like this. And now obviously our hypothesis is that if we increase the uncertainty in perception, people should use more environmental constraints than if they have perfect vision. And here are 2 videos side by side. On the left, you see the person with perfect vision. And you see that really the hand just focuses in on exactly the screw that has to be picked up. On the right, you see that the person is very uncertain, puts the hand down on the tablet to the right of the object, and then slides across the surface to capture the screw. So this is obviously just anecdotal evidence, but well, let's look at the data here. You see the table. The person is sitting at the bottom looking upwards. The screw is located in the square, and you see the traces of the different contact points. So it's easy to see that on the left-hand side, with perfect vision, there are only 3 contacts, and they're very brief contacts with the surface. On the right, there are 4 contacts, and there's a large sweeping motion. At the same time, the force has increased, so there's a higher force onto the table. The duration of the interaction obviously has also increased, and all the measurements that we use to characterize this exploitation of environmental constraints have increased. This is true for all the subjects that we tested and pretty much all the experiments. So there's a very strong correlation between uncertainty in perception and exploiting these environmental constraints. So to us, this is encouraging. We see this as support for our hypothesis. But now, as roboticists, we're left with sort of a dilemma, because many of the things that we've developed over the last decades maybe not, are not fully applicable any longer, right? We've always talked about configurations, right? We're placing contact points on objects. So this is sort of a static view of grasping. Now we have a very dynamic view, sliding along things and moving until some contact event happens. So there's a new way of looking at grasping, I think. All right, so now obviously the next thing is let's try to take this insight into the realm of robotics, and let's build hands that can do this. So we tried this, and this is the hand that we built. This was published at RSS this year, and I'm very happy to say that it won the Best Student Paper Award. It's basically modeled after the hand of my student Raphael Daimel. And it's entirely made out of rubber, so it's made out of silicon rubber. The idea is this is very soft, very compliant, so you can very easily touch surfaces and slide along them. This is exactly what we want to do. These are based on some kind of actuator. We call it the Pneuflex actuator. It's basically just a balloon out of silicon, and we inflate this balloon. There are several sort of little tricks to guide the inflation. You see the red helix wrapped around, so this stops radial or limits radial inflation. Then there's on the bottom layer, there's some inelastic fiber embedded in the finger. And so if we blow this up, giving these limitations, the finger will bend, right? The inside of the finger cannot extend, the outside extends. So when we inflate this balloon, the finger bends. We've built a whole hand out of this. You see here the palm, which is very important for an opposable thumb, right? It is very important for dexterity. And you see that all of these actuators are made out of silicon and are very compliant and, and soft. So they can adapt to the shape of the environment and they can adapt to the shape of the object. So now we have this soft hand, and the intuition says that this is now very difficult to control, to really be dexterous. And so, you know, we tested this, and to show you some anecdotal evidence, this is a cylindrical grasp that we were able to obtain. For all of the grasps I'm going to show you, we basically just use 4 degrees of freedom for actuation, right? There are 7 chambers, but we couple 3 of them, so we have only 4 degrees of freedom. So this is a cylindrical grasp, there's a spherical grasp, there's a pincer grasp. So this is, you know, a little bit surprising that with such a soft hand you're able to achieve such a grasp. This is a tripod grasp and a stylus grasp. So we were very encouraged. There were 2, I mean, you may be familiar with the Fikes taxonomy. It's a taxonomy of human grasps consisting of 32 different grasps. We tried to replicate those. I'm going to show you the 2 failures. On your left, you see a failure because, you know, the fingers cannot bend onto themselves, right? So holding a thin object with one finger is difficult given the way that we construct the hands. And on the right, you know, holding and using scissors is just extremely complicated. So we were not able to replicate this. But these are the 31 out of 33 grasps that we were able to replicate. And you can see that, that basically there's a huge variety of grasps. And we were able to almost cover the entire Fikes hierarchy using our first prototype. Now, when we analyze the space of these grasp postures and find out the intrinsic dimensionality of this space, and then compare that to the 4 degrees of freedom of actuation, we would expect that this space should be somewhere, you know, in the same ballpark. But it turns out that actually the space of grasp postures is much higher, has a much higher dimensionality than our actuation space. Where does this come from? It comes from the fact that the hand is able to comply to the object that it's grasping, and it differentiates its grasp posture in response to this interaction. So not only does this softness in our hand enable you to exploit these environmental constraints, I would also claim that it actually helps you be dexterous. And this was actually rather surprising to us. So to make a little reference to the presentation that we saw earlier this morning, the plenary note, you know, the speaker was asking for lightweight, very robust hands. And I think, you know, this hand weighs about 120 grams, so it's like a bar of chocolate. And really, you've probably had thousands of grasping experiments with this hand, all in contact with the environment because that's the purpose. So doing the thing that would break most robotic hands, and we really never have experienced a failure. If it would fail, it would probably be due to a puncture in our balloon fingers, and you just take some glue, stick it on it, and you're ready to go. So it's, you know, it's cheap to make, it's light, and, you know, maybe this is an interesting way to go for prosthetics. But as I mentioned several times now, this hand is very soft. And it's very difficult probably to control the hand or the fingers to go to a particular position. So the idea of deliberately placing contact points on the surface of an object is sort of out the window, right? So all of the main grasping algorithms that we've developed over the past decades cannot be applied. We simply cannot control this hand with sufficient precision to actually realize these grasping points. So we need also some new ideas about how to actually plan grasping motions. And I want to show you, you know, the initial attempts that we have made into this direction. So let's look at a scene. This is a Connect image of an office scene. You see on the left sort of a table surface. On the right, you see one of those rolling containers with drawers. There's a monitor. There's some things on the table and so on. And there's an object circled in red, which is the object that we would like to grasp. the assumption of our planning algorithm is that this object has been segmented and we know that it's there and, sort of that it's different from the environment. Now, we would like to pick up this object using environmental constraints because we think that picking up objects using environmental constraints is much more robust than without using environmental constraints. In this particular example that I'm going to talk about, I just want to use this sliding to the edge and then picking up of the edge grasp, right? This is something that humans do with flat objects. You slide it to the edge of the surface and then you pick it up. So this is the grasp that we want to do. Obviously, what we need is based on this RGBD connect image, so we have a point cloud, we would like to infer all the different edges that we can use for this grasp. So here you see the output of one of our planners, and in green you see the edges that it thinks it can use for grasping, and in red you see example hand configurations where this grasp can be performed. So this is obviously just one particular grasp around an edge. There are other things you can do in the environment. You can cage the object, you can visually servo to it, you can slide it, and all of these primitives we implemented, and we developed perceptual primitives to detect where in the environment these controllers can be invoked, and then the result of this is this graph. In the middle you see the green spot. This is basically the hand being anywhere in the world, being able to see the object we want to pick up, so we can use visual servoing to get there. If you follow the arrow to the top right, to the node C1 in purple, you can see that this is an object cage. So we can visually servo to the object and cage it. Then you can follow to, let's say, the orange node S4. This is a slide. And if you follow the slide, now you can access EG13, the blue node on the top, which is an edge grasp. So following this, based on this 3D point cloud, using our perceptual primitives on this data, we can derive this graph of where in the world can we do which of these controllers. And the result is this graph, where two nodes are connected if my hand can be in a configuration that maintains one environmental constraint but transitions onto a different one. And the result is this graph, and you see it's a moderately sized graph. Obviously, search on this graph for a solution path is no problem. And well, then we can output the plan. The plan is shown here, projected here into the scene. It starts with the blue thing, which is the visual servoing. Then it changes color to indicate that now there is a cage going on. This is the cyan. Light green is the sliding, and then the red ends of the arrow are the edge grasps. And the purple ones are wall grasps, where you push something against the wall to pick it up. So now, based on one single connect image, we have a sophisticated manipulation plan for picking up an object in the environment. And we can even use this plan to decide which branch we're going to take depending on what actually happens when we interact with the object in the environment. One way of visualizing this is illustrated on the right. Every one of these motion primitives can be viewed as a funnel, where we interpret the wall of the funnel to be the environmental constraint that guides us into a particular state. And the output of that funnel is within the domain of attraction of the next funnel, and so we can invoke the next controller. So basically, we're planning in a space of funnels that are sequenced to get to a robust grasp. Every funnel is robust because it uses this environmental constraint to ensure that you remain within the region of attraction. And if you use such a planner, this is actually not a planned path. This is a hand-coded path, but this is just to illustrate that you can use environmental constraints as sliding down the wall, sweeping along the bottom of this bowl, and then using the wall to pick up this candy bar. So there's a series of environmental constraints that are very easy to exploit because our hand is soft, and that lead to a very robust grasp, irrespective of how we place this candy bar inside that bowl. So basically, to come to the conclusion, I think that the soft manipulation, right? Manipulation with soft hands, exploiting the environment of constraints, is an interesting way of looking at the grasping problem that is motivated by humans. So Why should we do it in robotics? Well, because humans do it. This is what we illustrated with these experiments picking up objects. You see on the top right, Jose Alvarez Ruiz, and on the bottom, Marianne Mertens. These were the people that were involved in our human studies and analyzed the data. We have built soft hands following this idea of exploiting environmental constraints. The person, I mentioned him before, who built these hands is Raphael Daimel. And finally, I've showed to you the work of Clemens Ebner, who is developing these perception and planning algorithms to exploit these environmental constraints using soft hands. And with that, I think I have 1 minute left, so maybe time for one question.
So we really have very short question time.
Very nice talk. I think that the concept is very useful. One thing that I was thinking, if you have to pull up things which are heavy, use your skeletal system, right? Mm-hmm. Are you thinking about a hybrid solution in which you would combine this with something which could become hard? I mean, mechanically, you could get this rigidity?
Yeah, we're going to submit this to the next deadline. So we've built this hand with a dual chamber system, and one chamber can be used to stiffen the finger. So we can close the hand and then sort of freeze it in place, or make it, finger stiff to push against something. So yes, absolutely right. We've done that.
What's the actual payload of the soft hand?
The payload for this soft hand is probably about half a kilo.
Okay.
So about 4 times its own weight. But you can make stronger rubber and increase the air pressure to get to pretty much any force you want. I mean, you can crush trucks with this mechanism.
Great. Thank you again.
Good morning. My name is Nicolas Rojas. I'm a postdoc at Yale University, working with Professor Aaron Dollar. I'm going to talk about our work on precision manipulation analysis. By precision manipulation, we consider the kind of manipulation in which a glass object is repositioned within the hand-word space where a breaking or changing contact. These are some examples of this kind of manipulation. So given a robot hand, for example, this three-finger hand that is a very popular layout in our community, what we want is to determine the feasible movements to reposition any glass object within the hand-word space without breaking or changing contact, and at the same time, to define which of these possible displacements can actually be controlled by the hand actuators without depending on external factors to the hand. So we call this precision manipulation analysis. And the issue is that precision manipulation analysis is in general an impossible task using standard models for grasping analysis. So for that reason, in this work, we propose a precision manipulation analysis method that is based on the kinematic analysis of the closed kinematic change associated to the hand object system. I'm going to use this two-finger hand to simplify very quickly our method. The first step is just to model the contact between the fingertips and the object as spherical joints. This is kinematically equivalent to point contact with friction, and it was an idea initially introduced by the groups of the Gray, Bernard Roth, and Kenneth Hahn. The second step is to translate the hand object system into a closed kinematic change and compute this mobility. The third step is to construct the corresponding graph of kinematic constraints. And finally, the fourth step is to reduce the resulting graph of kinematic constraints using the Irby's group theoretic approach. So following these 4 steps, we define the general displacement characteristics of any glass object relative to the palm. Now, if we want to determine which of the displacements can actually be controlled by the hand actuators, we just lock the actuators, repeat these 4 steps, and the resulting displacements are those that cannot be controlled by the hand actuators. So, for example, for our two-finger hand, it results that the rotation along the axis defined by the contact points cannot be controlled by the hand actuators. So if you're interested in more details about this work and perhaps in knowing the results for the three-finger hand, I would love to chat to you in the coming interactive section. Thank you very much.
I'm Miyako. Our topic is encoderless robot motion control using vision sensor and back electromotive force. In these days, there are many robots for multitask. These robots have some merits such as accuracy, robustness, and repeatability. However, they tend to be heavyweight, high cost, and require many elements. In order to approach this problem, our concept of system integration is minimum system realization. We think robot designed by fewer elements in order to perform a single task is better. Advantages of simple robotic system are easy maintenance, low cost, and high reliability. In this study, we considered a visual feedback control system from a viewpoint of minimum system realization and proposed encoderless robot arm system. As you know, there are many research about visual feedback control for robot arm. For example, position-based visual serving. This method requires a large number of calibration and precise joint angles. And generally, image-based visual serving is known to have a local minimum problem. On the other hand, we have already proposed stable image-based visual serving. It does not require precise visual error on each image. In this research, we show precise joint angles are also not necessary for this method. Because our proposed method does not require precise joint angles, encoders are not necessary. In this research, we use DC electric motors and joint angular velocity of them are measured by use of back electromotive force. We estimated these three parameters and calculate joint angular velocity from voltage and current, and joint angles are found calculated from joint angular velocity. This is our robotic system. This simple system costs only about $200, and it is very easy to use because we can set up camera roughly like this movie if camera can get visual errors. Using this system, we realize precise motion control. The final position errors are 1.0 mm or less without any calibration and encoders. We think this method is suitable for practical use. I'd like to talk more detail about our research at the interactive session. Thanks for your kind attention.
Good morning, everybody. My name is Christian Ott from the German Aerospace Center, DLR, and I present work with Thomas Wimberg and Ms. Florik Jasinska. The work is about humanoid compliant whole arm dexterous manipulation, and it includes the controller design and some experiments. So the motivation of this work is to use whole body manipulation in order to operate some bulky and heavy loads. And in whole arm manipulation, it was designed as a method in order to basically wrap with the robot around an object in order to grasp it. And this, in principle, can significantly improve the load distribution because you use some structural parts of the robot in order to perform the grasp. And in this work, we employed some results from grasping control to this situation. And the main contribution of the work is the proposal of a new impedance controller, which is designed at an object level. So it utilizes an object frame for the grasp object. And the controller is able to distinguish between different types of contacts. So passive contacts like you have it at the chest, or active contacts like you have it along the structure of the arm. And this is utilized in the force distribution. The controller basically utilizes an object frame which is located in the passive contact point, so here at the chest, and this allows to relate motions of the object with rotations around the origin of this frame. And the controller itself has a basic, rather simple structure. It utilizes a Jacobian transposed approach with different control components for the object motion, for some coupling springs, and an additional term for the force closure in order to ensure the grasping. And these terms I can explain you in more detail during the interaction session, if you like. Here I would just show a few videos which show the final results. So in the left video, you see the robot grasping and lifting a bulky object, while maybe on the right-hand side, a bit more interesting, you see different stiffness behaviors where the robot shows a compliant behavior in one direction and the grasp object behaves in a soft, more stiff behavior in different other directions. So with this, I'm at the end, and I thank you very much for your short attention.
Hi. Hi, I'm Ian Bullock, and I'll be discussing our work on human precision manipulation. So I really want to just thank Oliver Brock real quick for kind of doing a very nice job setting the stage for this general type of work. Specifically, I believe also that we can gain quite a bit from studying the human strategies for manipulation and applying those to robotic systems. So, for example, with robotic finger designs, I think that often robotic hands will use sort of one main contact surface rather than using a more continuous range of contact surfaces. So the question I wanted to get at with this particular work is, in the case of the human, with human manipulation, what contact surfaces do we actually use? And how can we gain some inspiration from the human contact surfaces used to implement that for more versatile robotic systems? So specifically, the method I used was to have 19 participants manipulate a small spherical object with either 2 or 3 fingertips. And I use visual feedback methods to help them stay motivated to explore their workspace effectively. So having recorded all of these object positions and fingertip positions, the method I then used was simply to project the object position back into the local coordinate frame of the fingers. And what this lets us do is look at the range of angles which we can then project onto a sphere over which each fingertip is used during the manipulation. So if we take a look at that, looking at the thumb, index, and middle fingers, a few things stand out in the results. One of the things that stands out the most is the usage of the middle finger, which is actually quite far onto its side surface. And it's really quite interesting because I think in robotics, often we think about using hands and fingers in the direction that they can actively be actuated, in the directions that they can actively apply forces. But here we're finding a case in the human system where the finger is used in more of a bracing role, where it's actually the passive stiffness of the finger that is partly enabling the manipulation motions that we perform. So I'd be happy to discuss the other results in more detail during the interactive session. Thank you.
Hello, good morning, everybody. My name is Mahmoud Tawakkoli, and I'm within the Institute of Systems and Robotics of University of Coimbra from Portugal. I would like to present you my paper entitled ISR Soft Hand and Adaptive Underactuated Anthropomorphic Hand. I would like also to thank Oliver for the nice talk. He made the past easier for me to describe my work. So commercial processes hands, as you saw in the talk in the morning, are expensive and hard to use because of the control complications that, as you see here, some of them because of a lack of number of inputs, use a mobile application or the foot pedal for controlling the hand. And many people start to abandon using of that, even so that they spend more than $10,000 for those hands. So we want to make hands which are low cost, lightweight, simple in terms of mechanics and control. Like what Oliver told, we think the path is to go to the adaptive and soft mechanisms that result in lower number of actuators, simpler control, and simpler mechatronics. Inspired by previous soft hands, Mecha, which use cellular elastic actuator, and these two hands from PISA and STM hands that use compliance on the joints directly. We were inspired mostly by the STM hands, and we designed our ISR soft hand, which has compliant joints, 10 degrees of freedom, and only has 3 actuators, which you can see the first prototype, the hand here. This shows some of the experiments, including grasping an egg that is not cooked without having any tactile sensor. And this is the result of the 33 grasp that, again, like Oliver, we can do 31 grasp out of the 33 grasp. And finally, I would like to show you a short video of the hand that does only show some of the grasp. If you are interested to see more videos, I would be happy to take to discuss between the interactive session. So as you see, here we have only one, using only one synergy that you see is from opening to the closing, only on and off, and adapts to the following 7 objects. So when we fine-tune this synergy with some fine adjustment, can do 20 grasp out of the 30 grasp of the fakes grasp list. So this is a tip pinch. As you see, a large or a small objects are treated equally. We have only one signal, which is open and close. And now we do the lateral pinch. We only change the synergy a little bit. So okay, the time is running out if you want to see more. Okay, thank you.
Hello, my name is Yun Yijia from Michigan State University. So my paper is about the coordinated motion control of a holonomic mobile manipulator for the accurate motion tracking. Mobile manipulator can be applied to many areas. The accuracy of such system is a problem because the system, the mobile platform, and the manipulator are different. Traditional methods consider the mobile platform as additional joints and links of the standard manipulator. Such methods cannot maintain the accuracy of the end effector because of different errors. Usually the manipulator is more accurate and different dynamics. Usually the manipulator is faster than the mobile platform in the dynamics. So our paper aims to address these 2 issues. For different errors, we use the weighted student inverse to replace the student inverse, and online determine the weight to put more preference on the more accurate onboard manipulator than the mobile platform, on the onboard manipulator than the mobile platform. And for the different dynamics, we introduce an online coordination controller, a planner, to generate the input for the system based on the output of the mobile platform and the manipulator. So basically, the system planner is a closed loop and online. It will generate the input based on the output. And the generation will based on minimizing the coordination error between the mobile platform and the manipulator. Then we did experiment. Compared to the traditional method, the new method can reduce the maximum error of the end effector by 90% and the average error by around 60%. Here we also show a video to use our method in teleoperation. So in teleoperation, basically the operator only needs to concentrate on the motion of the end effector, and the motion for the mobile platform and the manipulator will be automatically generated based on our proposed method. And the accuracy of the end effector can be maintained, so it's easy and convenient for the operator to finish this task. So basically, with our proposed method, we can reduce the accuracy of the end effector of the mobile manipulator in presence of the different dynamics and the different errors of the mobile platform and the manipulator. So thank you.
So hello, I'm Johannes Stark, and I'm presenting joint work with Kaju Heng and Danica Kragic from the KTH Royal Institute of Technology in Stockholm, and we still believe in contact-based grasping. Okay, this paper is about generating position graphs on complex object shapes, graphs that you can see like this ones, and what you can see is that all of these graphs are actually fingertip grasps, and usually these graphs are generated with a sampling-based approach where you generate grasp parameters and you execute a fixed policy to establish the contact. In this paper, we are trying to do the same thing, but with contact level optimization. That means we have to deal with a very large search space and objective functions which are not convex in that space. And therefore, we are considering a representation that integrates the 2 most essential parts to a contact, which is the object and the fingertip. And this representation, we call it a fingertip unit, which is basically every available position on an object where you can place a fingertip. And when we extract this fingertip space from the object, we are considering both the local object geometry and the fingertip shape. And Here you can see on all these blue points are positions where the finger could be placed, and sometimes they're even overlapping because the object is very flat and smooth in that region. And in some regions, indicated in red, are regions where the fingertip is not compliant with the surface and the finger cannot be placed. And on these places, no fingertip units are generated. The optimization procedure applies a coarse to fine approach, which in other words means we have a multi-level refinement heuristic that is built on a hierarchy of increasingly simplified representations of the fingertip space. And in the top level, we start with an hill climbing algorithm. And the solution on each of these levels is projected down to the next simpler level, and at the end you're reaching at a contact level grasp, as here shown on the bunny. And every time we run this optimization procedure, we apply a objective function which both includes the reachability of the hand and the quality of the graph. So in the end, we have a graph that is both reachable and stable. This technique can also be applied to partial point clouds as long as the point cloud exhibits enough details so that the fingertip can stably be placed. And if you want to talk about this, meet me at the presentation stand.
Good morning. My name is Sergio Aguilera, and I'll present our work on modeling of skid steer model manipulators using spatial vector algebra and experimental validation with a compact loader. In Chile, the mining industry is very important, but at the same time, it's very dangerous. LHD and similar machines use skid steer platforms because of their simpler mechanics, high reliability, and better mobility in rough terrains. We can see these machines as skid steer model manipulators, and if we want to automatize them, it is essential to have physically accurate dynamic models, which can describe in a realistic manner the mechanical behavior and energy consumption, which are key aspects for the controller design. Our work focused on getting the explicit equation for dynamic modeling of skid steer model manipulators using Fairstone articulated body algorithm and the spatial vector algebra approach. The main consideration of our model are a 60OF floating base, which can move in any direction, and an NDOF manipulator attached to the top. Also, the wheels are modeled with non-permanent contact points. This allows us to study the wheel-ground interaction, wheel slippage and lateral skidding, and the base-arm interaction due to internal and external forces. Also, general geometric parameterization is useful to easily reconfigure the topology of the machine. The model was simulated using the spatial toolbox for MATLAB, while measurements were obtained during field experiment using a real compact loader CAT262C, which was modified to work remotely. A straight line and rotation motion data was acquired using inertial sensors mounted on top. The simulated data was compared to the acquired measurements in the field experiments, and they show a good level of consistency, thus validating the dynamic equations and the modeling approach. Also, the simulation results shows the arm-base interaction. When the arm is accelerating, when the base is accelerating, the arm position shifts, and when the base decelerates, the arm shifts in the opposite direction. Also, the vibration introduced by the wheels approximation due to the polygonal approximation of the wheels can be seen in the arm as a disturbance. We would like to invite you to see us at the stand and talk about our contributions and show you the full model and the explicit equations. Thank you very much for listening.
Good morning. I'm Kendall, presenting some work on trying to combine sensor data with a physical model to hopefully get a better estimate of what a robot might be doing. So it's our belief that to get fully dynamical behaviors, we need to calculate over a fully dynamical model. So simplified models may not give us the best estimate of what's actually going on. And obviously, for this to happen in real time, we need trade-offs between how accurate this is and how fast it might be. So Let's start from saying if we have a full trajectory of sensor data, we can optimize a state trajectory that matches what the sensor data sort of is giving us. And as you can see, we're trying to predict accurately the contact forces, the little red disco lights. But so obviously doing this sort of smoothing over the whole trajectory is impossible for actually controlling the robot in real time. So what we do is we take a smaller window of these sensor measurements and comparing them to a generative model from our physics engine, MuJoCo, we can optimize for this smaller time window that still gives us a better current time estimate. So obviously there's trade-offs between how large our window is versus how quickly we need this data. So to prevent these windowed estimates from drifting, we apply a recursive prior, sort of in like a EKF model. So what this gives us is some pretty good results with leave one out experiments where we generate our predicted sensor measurements, that's the lines in red, and compare them to the real sensor data when we leave that sensor data out of the optimization. And furthermore, our results for a real robot demonstrates that this physical behavior can be consistent even in basically the whole dynamical range of action that the robot may be able to accomplish. And so this is running on our lab's Darwin, which is, the cutest and biggest robot that we have. So there's a lot of little details for how we got this all working and got this working in a quick enough fashion. So please feel free to come by and we'll chat about robots. Thanks.
Good morning. My name is Emanuele Baglini from University of Genova, Italy, and our work is a real-time distributed architecture for large-scale tactile sensing. Currently, many different tactile sensors are developed using different technologies such as capacitive, resistive, piezoelectric, organic, or so on and so forth. But there are not so many really large-scale implementation. Why? Because there are a lot of issues that must be addressed at system level. Our reference tactile technology is the outcome of the RoboSkin project, and here you can see a patch, for example, where there are some interconnected triangular modules, each one with 12 capacitive tactile elements and electronic to acquire the data. Each patch is interconnected to a microcontroller that is able to acquire the data and send through a bus to a PC for data processing. So the system that we can see here is based on sensors. There are slave modules that acquire the data from the sensors, a bus that interconnects all the slaves to the master node that is able to acquire the data and process the data and use, for example, for the control actuators of the robot. In our previous work, we demonstrated that for this particular application, EtherCAT can be chosen as the most promising technology for this specific application. What is EtherCAT? EtherCAT is a modified Ethernet-based communication bus with real-time performance. It uses standard cabling, standard Ethernet frame. It uses standard master Ethernet board, and it uses a modified version of Ethernet in the slave that is able to process the data on the fly. Main goal of our work is the performance evaluation of the distributed network of the distributed network. So we built a mathematical model to measure the cycle time, to evaluate the cycle time in different configurations. For example, redundant, non-redundant topologies, physical, and logical addressing. And we test our model to validate it. The mathematical model is useful to evaluate the cycle time. That is the time that is required to acquire all the data from the master node. At the end, we validate our model with a physical test that perform us to measure the delay, the overall delay and jitter of the system. Thank you for the attention.
Hello, everyone. My name is Moussa Benuar. I am a robotics PhD candidate at Lille in Montpellier, France, and I'm here to talk to you about the work that I have done with my supervisors regarding a new control strategy for parallel kinematic manipulators. The desired compensation adaptive law, which is simplified abbreviated, abbreviated DCAL, is a very interesting control law designed for mechanical manipulators. It is basically inspired from an exact compensation of the linearities adaptive control by only replacing the actual trajectories by desired ones. This is of tremendous importance in robotics, since the complex nonlinearities are very heavy for the system. So, the work that we have done, we have proposed to replace the linear gains, as you see in the original decal, the Kp and the Kd, which are linear gains, by nonlinear ones. This work was inspired from the recent works of Wei Sheng, which presented new extended computed torque and new extended APD controller by simply replacing the linear gains in the original controller by the nonlinear ones. So here in this figure, you can see the comparison between the linear action and the nonlinear action. The linear action is in green, and the nonlinear action is in blue. So basically, what we expect from this controller is to achieve better tracking performance and lower control efforts. Moreover, in order to adapt this strategy to redundancy actuated manipulators, we propose to do a projection of the output of the controller using the kinematics of the manipulator. So here you see the schema block of the proposed strategy. So in order to validate this strategy, we propose to implement it on a redundantly actuated parallel manipulator available at our lab. And the results were promising for both scenarios, a nominal case and the payload handling. So we achieved, as you may see in the figures, an improvement of the tracking accuracies up to 10%. Also, the tracking efforts were significantly reduced. Thank you for your time, and I would like to discuss with you with more details this work in the interactive session. Thank you.
Good morning. I'm Youssef Mezouar from Institut Pascal in France. This work has been done with my colleagues Rodolphe Gour and Grégory Gogou. And the paper deals with structural synthesis of dexterous hand. The main idea is to exploit the theory of structural synthesis in parallel robotics area and for the structural synthesis of dexterous hand. So the goal is to synthesize dexterous hand structures with desired force closure grasping ability and fine manipulation ability. So in the paper, there are two main contributions. The first one is to propose a complete procedures, which takes into account all the structural design parameters as mobility, connectivity, over constraints, and redundancy. And also, it provides an exhaustive list of possible architectural structure for dexterous hand with respect to a set of parameters we give to the method. So also, the second contribution is that it allowed to fix some bugs that other dexterous hand synthesis methods we have by providing a correct mobility formula of mechanism. So this formula of mechanism gives the mobility with respect to joint mobility, contact finger connectivity, or object palm connectivity. So the method it can be divided in 6 steps. The first is to provide a set of parameters. The first 5 steps is to provide a set of parameters. So we have to choose first the desired number of fingers, to decide the characteristic of the finger trips, to choose the connectivity, the operational velocity space, the redundancy and over constraint degrees, and to choose a joint structure of fingers. Then, to synthesize the architecture of the end, we use evolutionary morphology, which can provide an exhaustive set of structure with respect to this set of parameters. So here are one example of a dexterous end structure for grasping with 3 translational degrees of freedom. We can note that in this case, none of the previous formula of mobility can give the good result, except the one we showed previously. And some other examples are here for 6 degrees of freedom and manipulators with a 3T3R architecture. And another example, which is a 3 degrees of freedom and structure with a structure 2T1R. Thank you.
So good morning, everyone. I am Marc Boutepard, and I will present this work, which has mainly been done by my PhD student, Nguyen Nguyen. It's entitled Study of Reconfigurable Suspended Cable-Driven Parallel Robots for Airplane Maintenance. So cable-driven parallel robots are a particular type of parallel robots in which you replace the rigid legs by cables. Some examples are shown on this slide, and the 2 distinctive characteristics of such robots are they can be used in very wide workspaces and manipulating very heavy payloads. So currently in a European project called CableBot, we are considering them as a possible means to replace more conventional crane-like machines to work in airplane workshops and also construction workshops. And we are considering reconfigurable cable robots in the sense that the wheel chains can move along rails, for example, or be repositioned at specific locations. Reconfigurable suspended cable-driven parallel robots should have the following advantages for the airplane construction and maintenance. I mean the advantages shown on this slide, such as the lower cost of construction and operation. In this work, in this paper, we are considering a particular 8-cable suspended CDPR architecture, which has been previously presented in ICRA last year. And we are using 2 performance criteria to assess the performance of this robot. One is related to power consumption, which it is the sum of cable tensions. And the other one is related to stiffness being probably the main disadvantage of such a robot in this application. And these 2 criteria represent the trade-off, which is illustrated in the paper by a case study. So on the top left, you can see results obtained by minimizing the sum of cable tensions. Basically, the cable tends to be as vertical as possible to evenly distribute the tension among the cables. And on the top right, you can see the result of optimizing the stiffness, where the cables tend to be vertical to optimize the lateral stiffness of the robot. And in the paper, we are using very classic multi-optimization tools to provide to the user some reasonable choices of reconfiguration parameters in between these 2 extreme minimization of the 2 criteria. And I would be happy to discuss that with you in the interactive session. Thank you.
Hi, my name's Kristen Marlow from Deakin University Centre for Intelligent Systems Research in Australia. My paper on the workspace analysis of 2 similar 3-degree of freedom axis symmetric parallel manipulators. This paper highlights the locations and types of singularities present within the workspace of these manipulators, followed by an examination of the manipulator's workspace size and dexterity. So first of all, what is axis symmetric? In this context, axis symmetric means that the robot has a common axis of rotation, which, as you can see in the video, will allow the possibility of infinite rotation. It also means that they have equal property in all closed radial half planes, as shown in the figure on the left. So these are the 2 similar manipulators. Due to the parallelograms on chain 3 and on chain 2, or on chain 1, and also the revolute joints along chain 3. This allows a simplified model to be derived, assuming constant pitch and roll. So joint rate and singularity analysis was performed. Um, First of all, the joint limitations were analysed, shown in red here. Then in figure 1, you can see the locations of the type 1 singularities. Figure 2 shows type 2 singularities, which are yellow, it's a bit difficult to see here, and purple. Figure 3 shows a magnification of the purple type 2 singularities, just showing that they lie just inside the boundary of the workspace. So by selecting appropriate parameters, it's shown that this manipulator presents a large singularity-free workspace. So this was followed by the workspace size and conditioning analysis. Using a genetic algorithm, we analysed the singularity-free workspace and maximised that. And this was followed by a maximisation of the global conditioning index. So this clearly demonstrates the trade-off between obtaining a large and dexterous workspace for this manipulator, and it also gives a lot of insight into the distribution of the conditioning within the workspace. Thank you, and I look forward to hearing from you and speaking to you in the interactive session.
Good morning. My name is Amin Aribi from Poitiers University. My talk today is about the improvement of the direct kinematic model of haptic device for medical application in real time using an extra sensor. So here present a new approach to overcome the singularity problem of parallel robots. Then the motivation of this work is the development of a teleoperation system for mini invasive surgery application. So here we focus on the master station composed of haptic device having a parallel robot architecture. And in order to study the surgeon gestures performing minimally invasive tasks, we use the motion capture system. Then after analyzing this recorded motion, we identify the workspace of each instrument. And here the workspace is described by a cone with an apex angle of 26 degrees, also identify possible movements. So we have a 4-degree freedom, 1 translation, and 3 rotations. And then we propose to use a spherical parallel manipulator that is presented here for the architecture of the haptic device. But as now, the parallel robot have the problem of the presence of singularity in the workspace. Then we will propose to overcome this singularity problem in the workspace the use of an extra sensor. This extra sensor will offer a solution to overcome the presence of the singularity and without redesigning the manipulator. Then we have at all 4 sensors installed on the haptic device. Then after implementation of this approach, and we develop it over teleoperation system. The teleoperation system, the redundant sensor has improvement the direct kinematic computation, as well as the accuracy of the model in the unicity of singularity position. Then the orientation error is calculated between the master and the device. And so thank you very much and for your attention. And it's a pleasure to me to discuss with you the result in the interactive session. Thank you.
Hi, my name is Luis Figueiredo. I'm here to invite you all to see my presentation on switching strategies for flexible task execution for cooperative manipulation. I'll be very fast now, I lost some time. The general idea is to improve robot manipulation. So here we'll focus on collaborative manipulation. Well, collaborative manipulation, there is many benefits. I will not discuss it a lot because I have few time even now. So I'll go directly to the challenges. I first need to describe the arms kinematics. So here you use unit two criterions to represent the power kinematics. And I need to describe the cooperative framework, and we are using the cooperative dose text space for that. It allows us to describe the relative and absolute pulls between the arms. Well, we have done some contributions in this sense, and present some demos as well, and we'll be presenting this afternoon at the exhibitors' rooms at the Baxter booth. You are invited to join me as well. So the idea now is cooperative manipulation also adds new challenges. You have to avoid the collision between the loads, between the arms. You have increased liability of joint limits and singularities. And to cope with that, a good strategy is to use self-motion, to use the remaining free movements. So how to use reactive motion? For that, we are proposing this flexible task execution that instead of defining a fixed pose for the desired goal, we are defining a region. And in this sense, instead of defining a position, we are defining a cube where you can place your load in any point of this cube. And the same goes for the orientation. And you define it, you can tilt your load just a little bit, and you define how the tilt works, how can you tilt it. So the objective is obvious, to enlarge the new space and allow us to increase the reactive motion. You have to ensure stability, and for that we are using apps controllers. And our example shows that we could really improve the second task while holding the main tasks. Anyway, I'll invite the
The title is Vibration Control of 3PS4 class parallel mechanism for high-speed application using quantitative feedback design. And my name is Michihiro Kanishi from Toyota Technological Institute in Japan. And the Delta Keops is a relatively new type of Delta robot. And due to the number of the joint, motorized prismatic joint and number of passive spherical joint, the system can be classified as 3PS4 class of parallel mechanism. And this mechanism can realize the pure translational motion and has higher rigidity compared to the conventional type, like ABB Flex pickup. And as you can see in this video, even in this mechanism, at the very high speed, it still has residual vibration. So the research objective is to reduce such residual vibration. First, we consider open tree structure to apply Lagrangian formulation. In order to do that, to do this by cutting the link between the end effector and the base, then the equation of motion can be derived. And using this, we can linearize the system. And of course, the parallel link has a passive joint. So in order to estimate the angle of passive joint, we have to use forward kinematics and inverse kinematics. We also use the Jacobian to calculate the force from the open tree structure. And however, due to the unmodeled dynamics, the linearized plant has this kind of anti-resonance. That ideally, this should be double integrator. So in order to cope with this is one of the reasons of the residual vibration. So in order to cope with this, we collect the frequency response, and using QFT, so we designed the prefilter F and the controller G. So this is the last slide, so summarize the comparison. And the QFT controller can meet the specifications. The important thing is the proposed method is robust and systematic because they're both using dynamic model and frequency response data. Thank you.
Hello, I'm going to talk you about the synthesis, dimensional synthesis of 4 degree of freedom parallel robot, which is redundant and able to do shunt flies motion, and which aims at machining applications. So there is still barriers for parallel mechanisms and machines to be used in the industry, and these barriers are listed here with workspace limitations, singularity problems, sometimes complex designs, and also it's difficult to have at the same time accuracy and high dynamic performances. So mechanisms are very often specialized in one of these fields, like the two examples you have on this slide. And here we aim at machining application, and here is the preliminary design of the mechanism, which is redundant. It has 6 linear actuators, and at the end, the traveling plate, the moving platform, has 4 degrees of freedom with 3 translations and 1 rotation, which is unlimited. Here you have 2 parallelograms for constraining the unwanted rotations, and then also 4 simple chains to constrain the platform pose. The main characteristics are a large workspace for this mechanism, good homogeneous performances on all the workspace due to the actuation redundancy, rigid, very stiff design, and the design also is very, very simple. Okay, so here we are talking about the optimization of this mechanism, and I will give you more details in the interactive session. And at the end, for given actuators, the performances are isotropic linear acceleration guaranteed on all the workspace in all the directions of 8.5 Gs, an amplification factor for the accuracy, which is 4.5, and a peak acceleration of 24.5 Gs. So if you want to have more details, please come and see me in the interactive session. Thank you.
Morning, I'm David Weber from iCube Laboratory in Strasbourg, France, and I want to talk to you about active vibration cancelling of a cable-driven parallel robot using reaction wheels. Mark Goodford introduced this kind of robots. You have cables instead of rigid legs. So here is an example, the Skycam over a football stadium to film a match. We have huge workspace with this kind of robots, but due to very low stiffness of end effector, you are subject to vibrations. We model these vibrations, and we designed a robot with an end effector embedded power, actuators, sensors, and the computer, and use inertial feedback with an IMU to stabilize the end effector actively. The reaction wheels embedded are used to cancel the rotational vibrations, and for the translations, we used the motor pulleys. We designed controller by pole placement with an objective of disturbance rejection. So a planar robot with 2 pair of 2 cables is considered. We have designed a prototype robot and a realistic simulation. This robot is built with Lego Mindstorms, which present a lot of drawbacks to control point of view. The actuator saturation is low. We have a heavy drive friction and a high quantification step. We intend this as a worst-case benchmark, easy to reproduce. But we have interesting advantages, such as a really lightweight structure. So here are some results. Active vibration algorithm is working on the right. The excitation are realized with reference steps and pulleys position. We can see the effect of the single degrees of freedoms, horizontal and vertical. And then we have the 4 damping loops working together. The aim is to speed up the natural slowdown of vibration, not to avoid them completely, because the actuators are not sufficiently powerful. And finally, you can see the performance with end excitation when the whole control system is enabled. So for the robot design, we use a custom Simulink encoder target for the Raspberry Pi on Lego Mindstorms and available open source on our team website. And to finish, we are extending the work presented here on 6 degrees of freedom cable robot with 8 cables, and we have an active vibration counseling on all degrees of freedom. Thank you for your attention. I hope to see you on the interactive session if you have more questions.